right, man. Somebody's got to keep me straight. Okay. Well, like I said, somebody's got to keep me straight. All right. So basically, everything that we're going to talk about in the next couple of chapters is a lot of them are going to be. So I'm going to say like 90% of the things that we're going to discuss are actually going to be considered anemias. Okay. Not necessarily what I would consider an anemia, but the book considers them a type of anemia, okay? But iron deficiency anemia, and then we're going to talk about something called thalassemia later on. Those are really your true anemias, okay? Like they have low hemoglobin, they have microcytes, hypochromia, those kind of things. Some of the other ones, they consider them an anemia, but they're really not. I mean, like their red cells may be normal, they may be normocytic, they may be normochromic, which to me goes against the definition. But if you'll remember from the beginning of this that we started talking about, anytime that it interferes with red cell production or hemoglobin production, it's still considered an anemia, okay? So that's why, all right? So when we start talking about megaloblastic anemia, you're going to see that the cells are actually macrocytic and they're normochromic, okay? So there's really not a hemoglobin problem, but there is a red cell production problem. So it gets classified as an anemia as we go, okay? All right, but listen, iron deficiency is an anemia, okay? It's actually the most common anemia that we have in the world, okay? All right, so you guys, I know you're going to get mad at me, but I'm just telling you it'll help you. I'm not going to spend time on it, but chapter 11, that was before this one, you need to go and read it. At least read it, okay? Because it's an introduction to anemias in general, about certain characteristics and those kind of things. But then we're just going to go right on in and start talking about the iron deficient anemias, okay? So, anemia in general, defective hemoglobin production. This is a big one for us. Remember we talked about how our body's really, really efficient. So if you don't have the components, our body's not going to make what it needs, okay? And so in this case, that's exactly what's happening. If you don't have the iron that you need to be inserted into hemoglobin, your body's not going to make hemoglobin. Does that make sense? So therefore, if your body's not making hemoglobin, what's it going to do to your body? You're not going to get what that you need? Oxygen, right? So your body's going to be fatigued, you're going to be tired all the time, those kind of things. So this is a problem. So the things we're going to talk about in this chapter is we're going to talk about deficiency in iron in general. We're going to talk about defective iron metabolism, okay? So there are some things that you can't absorb iron like you should, okay? And then we're going to talk about defects in the porphyrin ring, all right? So that protoporphyrin 9 that we talked about that's happening in the mitochondria and the cytoplasm, anything that defects that or is not working properly, you don't get the porphyrin ring form, so therefore you don't have a place to put iron, okay? We'll talk about those. Those are actually called porphyrias. That's where the vampires come from. And you guys will see that when we get there, okay? And then we're going to talk a little bit about globin synthesis later on. This one is not really anemias. These are referred to as thalassemias. And we'll talk about that in just a minute, okay? Questions so far? We're good? All right, so most iron deficiency anemias result in microcytic hypochromic anemia. Okay, that's what you refer to IDA. All right, anytime I say IDA, what is the morphology in your brain? You ought to have microcytic hypochromic. Okay, so what does that mean? I'm going to have tiny red cells that are washed out. Right? They have a huge central pallor because there's no hemoglobin there. So, microcytic hypochromic anemia, IDA, iron deficiency anemia. Okay? From here on out, I'm just going to refer to it as IDA. Okay? IDA, iron deficiency anemia, is what IDA stands for. All right?
And describe it again.
Small red cells, microcytes, so small red cells. Hypochromia, washed out red cells. Okay, so they have that huge central pallor. So very little hemoglobin in them. Okay. All right, so causes of defects in hemoglobin production. So abnormal iron metabolism, and this is usually the big one that usually causes iron deficiency anemia. I know here in the West, we talk about the West and make sure we understand what we're talking about. When we're talking about the West, we're talking about Canada, U.S., Mexico, Central South America. In the East, of course, we're talking about really Europe and Asia and those kind of things, okay? So in the West, we don't have as much iron deficiency anemia as the East. Yeah, the East does, okay? And the reason is because we eat more meat than any other place in the world, okay? If you eat meat, you really don't get iron deficiency anemia that often, okay? But you have to always take into consideration female population, right? Because female populations from the age of about 10, you know, really and truly, there are 9 and 10-year-olds that start their cycles, okay? So 9 to 10 up to 50, you know, 55, you still are going through menstrual cycles. So therefore, that contributes to the larger number of IDA in the Western countries, okay, as you go, all right? So iron deficiency is usually, it usually is some kind of absorption problem. And when we talk about absorption, if you're not eating it, that's an absorption problem. Does that make sense? It's still an absorption. It's malnutrition, but if you're not eating it to absorb it, it's still considered an absorption problem, okay? Then we talked about the defective porphyrin metabolism, and we're going to discuss every one of these as we go, okay? I like this little chart. I know you guys might not understand it, but what we're going to talk about here is basically the anemias that we have, okay? So it's a really good chart if you'll look at it once we start talking about it. So like we talked about earlier, anything that has to do with the globin, okay, so chromosome 16, chromosome 11, any of those loci that are on there, okay, so the 6, 7, depending on how you do the gamma, okay, you know, any of those, if there's a problem with those, is not anemia, but it's called thalassemia, okay? There's a whole chapter on thalassemias, chapter 14, I believe it is, in your book. So we're not even going to talk about thalassemias right now, okay? So on this side is where we want to concentrate. We want to concentrate on heme production to make hemoglobin, okay? So iron deficiency, if it's an iron problem, you get 2 choices, okay? You have what we call iron deficiency anemia, which is the one we're going to discuss mostly here. And then you get anemia of chronic disease. ACD stands for anemia chronic disease. This is in your book, figure 12.1. And then at the bottom, it's got like a key that tells you what all these are. Does that make sense? Okay. Huh? Is it up here at the top too? Okay, cool. Awesome. All right. In your book, I think it's at the bottom, isn't it? Yeah, that was why I was confused. I just wasn't reading it up there. So IDA, or anemia of chronic disease. This one's also referred to as anemia of inflammatory disease also, okay? So any of those problems, if you have low iron, it leads to these disorders, okay? All right? So first, let me say this, all right? Anemia is not a disease, okay? It's not even a disorder. Okay? All right? Anemia is a symptom. Does that make sense? Okay? Anemia is a symptom. All right? The disorder is right here on this side. Okay? This is the disorder. Okay? This is a symptom of this disorder. Okay? So iron deficiency, iron unable to absorb iron, EPO, not making EPO, so like kidney failure, those kind of things, and then cytokines not working like they're supposed to, or enzymes in that heme process that we talked about, ferroketolase, you know, those things that are happening in heme production. If they're not there, that's the problem. It's not necessarily the anemia. Anemia is a result of those disorders. Okay? Does that make sense? All right? So I want you to understand that. Anemia is not a disorder. It is a symptom of a disorder. Okay? All right? So EPO production, if we have a problem with EPO, it also is considered that acute chronic anemia of chronic disease as you go. Okay? Cytokines. We talked about other cytokines. If those cytokines are not being produced, they're not going to stimulate EPO, then EPO is not going to play a role in making heme. And then, of course, those heme enzymes, all right, this one right here, SA, is siderotic anemia, okay? Siderotic anemia, either one of them. It can be sideroblastic anemia, which is what they usually look at, because that's usually what's affected in siderotic anemias. It's usually those erythroblasts in the bone marrow, okay? And then porphyrias. Porphyrias is a deficiency in enzymes, and so that porphyrin ring doesn't form, so therefore you don't have heme, okay? So in this chapter, we're going to talk about these things, all right? These are the ones that we're going to talk about as we go through. All right, any questions? And listen, I know it's a lot. I really do. And that's the reason, I've tried to tell you guys from the beginning, and I started even last semester, hematology is hard, okay, because it's a foreign world to you. You've never heard a lot of these terms before until you got to hematology, okay? You have got to study every day. You've got to read your notes every single day if you really want to ever understand this stuff, okay? And I hope you want to understand it because you're going to be doing it the rest of your life, okay? You've got to be able to do this for the rest of your life. Theory. It's got to be there, okay? Or at least the basics of it, all right? Because you do CBCs every day. Hundreds of them, okay? All right? So let's talk about iron metabolism. So iron's required by every cell in our body. And the reason it's required for every cell, we've also talked about every cell doesn't make hemoglobin, does it? Where does hemoglobin synthesis occur? What? Where? Where does hemoglobin synthesis occur?
Liver.
Oh.
I keep thinking the ribosomes, but that's not
Well, yes, it does technically happen in the ribosomes, but which cells does it happen in? Because it's a protein, and proteins are made by ribosomes, right? Yes, but ribosomes in what cells?
the erythroblasts.
The erythroblasts, there you go, that's right. Because they're the only ones that really need hemoglobin, right? I mean, now, there are some white cells that have a little bit of hemoglobin, but the majority of cells, well, the only cells that need hemoglobin are red blood cells. So therefore it starts in the erythroblast, and then by the time it gets to that reticulocyte stage, it's full, okay, as it goes. All right, but look, it says every cell needs iron, okay? So how can that be? Obviously, iron's used for what? Well, but that's happening in hemoglobin. What about other cells? So it also has to be in what? Other compounds, right? It's actually lots of things iron is in. Iron's in certain chromogens. You know what a chromogen is? What's the word chromogen mean? Color, right? Is that what you said? Good. Colors. Pigments. So any kind of pigment that you have in your body, a lot of those pigments contain iron. Melanin, for instance, that's the biggest pigment that most of us have in our body, unless you're an albino, and then you don't make pigment, right? You don't make melanin. Okay? But melanin is one of the largest pigments that we have in our body. There are others, beta carotene, there's some other kind of reds, pigments that we have, but they all use iron. There are also enzymes in our body that use iron, and they have to have it, okay? So that's what it's talking about when we talk about cells have to have iron, all right? Problem with iron, though, is iron doesn't flow good through our body. So for it to get there, we have to have proteins, okay? One of the big proteins is albumin, of course. We talked about albumin when we were talking about bilirubin the other day. But there are other proteins, and we're going to talk about those in just a minute, that help basically carry them to cells and bind to receptors to help iron get into the cells so that they can do what they need to do. Okay? So iron's in organic. Everybody knows that, right? Iron is inorganic. Everybody know what inorganic means, right? What's organic? Contains carbon. Inorganic is anything that doesn't contain carbon. So most of your single elements, or all of your single elements with the exception of carbon, of course, are considered inorganic elements. And so anything like salt, for instance, sodium chloride is an inorganic compound. Okay? So iron, of course, is inorganic. All right? Can be ionized. We know that because what do we use in heme? What form of iron is used in heme? Iron 2, right? So if it's iron 2, it means it's been ionized, right? And it is in the what state? Ferrous, right? Iron 2, ferrous. Do we use iron 3 in our body? Heck yeah, we do. Iron 3 ferric is what's actually known as non-heme iron. And it's for all this other stuff that we've just talked about. Okay? Questions about that? All right. Iron toxicity. We can actually have too much iron. And this is important to us because we actually will talk about a disease that's called hemochromatosis. Okay? Y'all ever heard that term? Of course you have not.
I have.
Have you?
I had a whole list on
I have my boss had that,
Really?
and they had to go draw blood out like every 2
Male?
months. Yes.
Yeah. It's usually male. There's rare times it's
And they
females,
knew
but
when it was
usually
time
males.
for him to get, because he was mean.
Did he get copper? Did he get a little bronze looking?
He was dark.
Yeah. A lot of times that's the way they see it, you know, is they start developing like a bronze tone to their skin.
He had to go every 2 weeks.
Yep.
He was doing it every month. That wasn't.
Well, that's good though, because I know people that do it every week. They have to have it
Well,
every
he
week.
ended up doing it every week.
Yeah, it usually progresses as they get a little older.
Mean when
Okay.
it's time.
So, hemochromatosis, all right, what is it? Hemochromatosis is an over-absorption of iron, is essentially what it is, okay? So our body actually is very, very efficient. So, we may eat steak every day, but we're not going to take iron in every day, okay? We may take a percentage. What percentage do you guys think we would probably take? Let's see how logical you guys are.
25.
Who says 25?
10 to 15%.
10 to 15% per day?
Yes.
Yeah, about that. Mm-hmm. Why do we take in 10 to 15%, do you think? It's actually a little bit less, but why would we have to take iron in? Huh? Yeah, well, what's our cells doing constantly, every day? They're dying, right? Because remember we talked about our red cells? We use about 1%, about 1% of our red cells a day. So, of course, heme is broken down, okay? And a lot of the iron is stored because we talked about it being recycled. But sometimes it doesn't. It doesn't get recycled. Or it gets put in some other pool or something else and doesn't necessarily make it back to the bone marrow, all right? So when it does that, so we really only take in about 1 to 2% a day, really, okay, as we go. So people who have hemochromatosis, their body has lost that ability to recognize, I don't need but 1% of iron. And so what happens is they take in all their iron. So every day they eat a steak, ever how much iron's in that steak, that's what their body absorbs, okay? So here it becomes a problem because remember how we talked about our body's really, really efficient? And what does it do with most of that iron? Make what? What does it make?
Blood.
Well, it doesn't make blood. It makes what? Hemoglobin. Okay? So if I've got all this excess iron, my body, the only thing it really knows to do with it is make hemoglobin. But if it's going to make hemoglobin, what else has it got to make? Now,
Blood.
blood. Particularly, which one?
Red blood.
Red blood cells, right? So basically, you see this cascade of increased EPO, all these other things that lead to more red cell production, okay? So if I have more red cell production, which one on my CBC or what 3 things on my CBC are going to be increased? Nope. What 3 things on my CBC will be increased if I have an overproduction of red blood cells? Well, first of all, RBC count, right? Then what? Hemoglobin, and then the other one, hematocrit, right? So those 3 parameters are going to be high every single time. So yes, it may increase those indices, the MCV, MCH, and all those other things, but the 3 big ones are red cell, hemoglobin, and hematocrit. Okay? So, if I have a hematocrit of 60 and 70, what does that do to my body? Increases my chance of having what? A heart attack or a stroke. Yeah. Because now instead of me pumping, blood that's normal and what my heart's designed to pump, now it's pumping motor oil. Does that make sense? Or really it's like pumping molasses through my veins. And so it's a whole lot harder and it's a lot of work on your heart. So you end up, what will happen is they might end up having a heart attack eventually, but usually what happens, they end up in congestive heart failure first because their heart just wears out. And so they can't pump that. All right? So you can get iron toxicity just because iron is toxic. Okay? As we go. So the more iron you have in your body, the more available. And especially that iron 3. Okay? Iron 3, the ferric form of iron, is very toxic to our body. So it has to be either converted to iron 2 or it has to be added or, bound to some protein or other chemical. Yes, ma'am?
Can, medications cause that? Because,
yes.
When a male's on, testosterone, ain't that really common?
Yes. There are lots of several of those steroid hormones that can actually cause hemochromatosis. Of course, it would be considered a secondary hemochromatosis because it is being formed by something else. It's not a natural. Because we'll talk about there's a primary, there's actually a hereditary form of hemochromatosis also. Okay? When we get there. All right? Low iron end results in inhibition of critical metabolic processes. That's what we were talking about before. So not only no hemoglobin, but also some enzymes that use iron. So anytime you have anemia, yes, you may have a low hemoglobin, but there's probably also some enzymes that are not being formed like they should too. So which is going to lead to problems. Okay? All right, so iron can't readily move across the membrane. So that's the reason it has to have those proteins. Okay? Enterocytes. You may know what enterocytes are. Have y'all ever seen this term before? You probably hadn't, and that's okay. Enterocytes are the cells that line your gut. So like your small intestine and large intestine. These are known as enterocytes. Okay? What about hepatocytes? They're your liver cells. It's liver cells in general. All your cells in your liver are referred to as hepatocytes. Now some of those hepatocytes have special names. There's one that's called Kupfner cells that we'll talk about a little later on. And then, of course, macrophages. We know macrophages are responsible for making cytokines and those kind of things in the bone marrow. Okay? So these 3 cells definitely have to have some proteins to help pull the iron into their body. Of course, the enterocytes, they're pulling it out of the food, right? So this is where digestion occurs. Enterocytes play a role in digestion. So the food basically gets broken down, and then it gets absorbed into those cells. So the only way it can get in there is to have proteins in our digestive enzymes. Okay? So RBC precursors use most of the imported iron, which is what we talked about before, and they do not export it. Okay? It means iron's never taken out, okay, by the cells. All right? 2 iron-containing compounds. All right? Functional compounds. All right? Metabolic functions and enzymatic functions. This is the 2 I want you to know right here. Metabolic functions and enzymatic functions. Okay? Metabolic would be hemoglobin, myoglobin. Those are the two big ones, hemoglobin and myoglobin. Okay. Enzymatic, those cytochromes, chromogens, any of those kind of things, they're there. And then, of course, there are compounds that serve as transports. That's what we were talking about earlier. Albumin does it, but the biggest transporter for iron is transferrin. All right, transferrin. I made mention of that in last chapter. Okay? Yes?
What's the difference between transferrin and transferrin receptor?
Well, transferrin receptor is what's going to be on these cells.
To get transferrin?
Mm-hmm.
Okay.
So essentially it'd be like this. Transferrin is a compound, it's a protein, and it would carry iron like this. Two of them on each molecule. Okay? So what happens is that you've got your cell, there's a binding site that this comes in and hooks into, and then it's brought across. Well, most of the time iron is the only thing that comes in, and then transferrin goes off in there. We're going to talk about that in just a minute. But yes, transferrin is the actual protein, but transferrin receptors are where they hook up on the cells to get the iron into them. Okay? All right, storage form. We've already talked about storage. This one mentions hemosiderin. What's the other form? We talked about it in the last chapter. Starts with an F also. I remember? Iron storage, two forms. Hemosiderin and ferritin. Good job. Hemosiderin and ferritin. Those are your two main forms of iron storage. Okay? All right. Questions about that, guys? Excellent. Okay? So, total iron concentration in the body is about 40 to 50 milligrams of iron per kilogram of your body weight. Okay? And I'm not good at my math. I think it's like, is it like 2.2 kilograms per pound, something like that? Is that about right? So you can figure out your iron storage if you know how much you weigh. I don't know that I can multiply that high myself in my head. I'm a big boy. Iron found primarily in those cells that we talked about earlier. RBCs, of course, in the form of hemoglobin. Macrophages in the form of enzymes, usually. There are some of those cytokines that have iron in them also. Hepatocytes, which are the liver cells, and then those enterocytes are the ones in the small intestine. Okay? So hemoglobin, of course, is the major fraction of body iron, which we've talked about all through here. 1 gram of iron per kilograms of RBCs, and then 1 milligram of iron per milliliter of RBCs for us. So you can kind of see how much iron there is. Okay? And a matter of fact, hemoglobin is what makes up the majority of the weight or the mass of RBCs. Okay? So if you took RBCs and like dehydrated them down, you would really, all you would have would be left is the hemoglobin weight. And the majority of the weight of hemoglobin is actually iron. I mean, that's the molecular atom has the most molecular weight is iron. Okay? All right, so here's a good little chart for you guys. If I was you, I'd be familiar with these here. Just kind of look at it, make sure you know what you're talking about. And you guys have seen some of these enzymes, whether you knew it or not. You guys have talked about catalases. You've talked about catalase before. If you were in biology, if you're ever taking biology, you talked about peroxidases. We have these little vesicles in our cells that are called peroxisomes. Okay? Peroxisomes contain peroxidases. Okay? Catalase and peroxidases both play a role in breaking down hydrogen peroxide. Okay? Is what they do. Why do we break down hydrogen peroxide? Why do we need enzymes to break down hydrogen peroxide? Oh. No. What is hydrogen peroxide? H2O2 is hydrogen peroxide. That's the chemical formula for it.
What's that for?
Huh? Ozone.
Oh.
Ozone is O3. So when is this going to get broken down into? It's going to get broken down into that. And of course, that's not balanced. You'd have more moles and that kind of stuff up there. But essentially, we need to break this down into this. Because this is toxic and this isn't, right? This is what we need. I said it's not balanced.
Okay.
It's not balanced. I said we'd have to have a coefficient up here to make it get what we need. But essentially, we need hydrogen and oxygen. So that's what we have to do. Does that make sense?
Yes.
So like you guys use catalase to determine what in micro?
The difference between a staff and a
That girl, staph and strep, right? So when you put that little drop on that colony and you saw those little bubbles, what was the gas? Being oxygen. It's oxygen being broken down. Okay? The reason we need to do that is because hydrogen peroxide is toxic to our cells. So if you get an increase in hydrogen peroxide in your cells, it kills them. So you have enzymes that break that hydrogen peroxide down. Some of the metabolic processes that we do in our body produce hydrogen peroxide as a byproduct, as a waste product. Okay? All right, so let's talk about iron distribution. So iron and hemoglobin remains in RBCs until the cells are removed from circulation. This happens in the spleen, of course. Can happen in the liver and the bone marrow, but more efficiently in the spleen. So 85% of this iron is recycled. So you still have 15% that you end up losing. Okay, that's the reason, like Carol was saying earlier, anywhere from 10 to 20% is what we absorb. Okay, now it may only be like 1% a day. Okay, as we go, but it is end up being a total of about 10 to 20%. The reason is because we don't recycle it all. We do lose a little bit of iron as we go. Okay, so iron is bound to transferrin, like we talked about earlier, as a transport protein, and then is delivered to the erythroblast in the bone marrow. Okay, and of course that is for heme production. All right, any questions so far? Okay. All right, so iron homeostasis. Do y'all know what the word homeostasis means? Balance. Huh?
Also say
Equilibrium. It's the same thing. Balance, equilibrium, remember how you want to remember it. Homeostasis. So what does that mean? That means we lose iron, we have to gain iron. Right? If we gain iron, we need to lose a little iron because we don't need too much of it. We like for it to be equilibrium. Okay? Balanced. All right? So, absorption of iron, total body requirements, these kind of things. All right? So, here's a weird thing. We'll talk about this in just a minute. Babies can develop what's called a physiological anemia, iron deficiency anemia. Most babies, somewhere along their way, usually about, we'll go out on a limb, I'm going to say anywhere between 5 months and 10 months. Babies go through this weird stage where they end up becoming anemic, iron deficient anemia. And the reason that they do is not necessarily, well, it is what's happening, is there's not enough iron in the formulas and not enough iron in breast milk for them to get iron. And their body is changing so much at those particular months in their maturation. I know that sounds crazy, but that's what it is. They're maturing, they're growing. So they end up depleting their iron stores. Okay? So a lot of people you have to get them iron droplets. And if you've ever had to give your kid iron, God, it's horrible. It's the worst thing in the world. It's like these little brown drops, and you put them in that. I was like feeding my kid, gagging, because of the smell. And he'd bite it and gag too, But he had to have it because he had gotten so bad anemic because of just growth. Just getting there, and he uses up all this storage. Okay? So it's actually called physiological iron deficiency anemia. So your body requirements are what's going to basically cause you to get more iron. Okay? Teenagers, especially guys, when they hit puberty, they actually begin to crave meat. Okay? I know that sounds crazy. I know we're living in a world where people want to be vegetarians and all this other kind of thing. But I promise you, metabolically, their body will crave meat. Okay? And the reason is because they're growing so fast and their body's changing so fast that they require more iron. And so they'll start wanting that iron and start craving it. Okay? All right, 2 forms of dietary iron. We talked about that just now. There's the non-heme form, is what we refer to it as a lot of times. This is the ferric, the iron 3. Okay? And then we have the heme iron, of course, which is the ferrous and the thing. So notice, all right, and I know y'all are going to be mad at me, but I told y'all I'm not real politically correct. Non-heme iron, which we can use for hemoglobin, is found in mostly what? Vegetables and plants. Okay? That's the reason if you are a vegetarian and you choose that weird lifestyle, you need to throw some vitamins in there. Okay? Especially iron supplements. Okay? Because you need that extra iron, but you need the iron 2 form, the ferrous form. If you can get it. And I think you can buy that. I think you can actually buy the ferrous iron. Okay? Heme iron, though, is found in good old red meat. Okay? Unfortunately, red meat's pretty bad for our cholesterol, though, usually. Okay? But I like red meat. I am a steak eater. You know what I mean? I am a hamburger guy. There is no fear of me ever becoming anemic. You know what I mean? Because I eat steak. Okay? But those are the 2 heme irons that you guys need to be familiar with. All right? And know where they come from. All right? So let me ask you this. So, Western civilization, we eat lots of this, right? Eastern civilizations eat lots of this. That's the reason they're little skinny dudes, right? It really is. They don't have cholesterol problems in China. Of course, they don't have a whole lot of food in China, but either way, food they do have is not usually steak. They're usually eating rice and, vegetables and those kind of things. And so that's another reason why you see a lot of anemia in Eastern countries than you do in the Western countries. Okay? If I had to eat with chopsticks, I'd be skinny too. You know what I mean? I've tried that. I ended up just putting them together and kind of shoveling it in. But anyway, okay. Non-heme sources, ferric complexes. So problem with the non-heme, though, is they're not easily absorbed. So you do have to have that transferrin molecule. The gastric acids that we have in our stomach, they actually help solubilize. When you talk about solubilize, what does that mean? Makes them to dissolve, right? Become soluble, all right? Low pH allows transport of iron across the enterocytes membrane, okay? So I'm going to say something weird, okay? Now, y'all don't think I'm crazy, but it's true. People who take like Pepsid, any kind of antacids all the time, have a chance of developing iron deficiency anemia. Okay? And the reason they do that is because it lowers their pH in their gut. And that low pH is what helps to get the iron actually across those enterocytes. Okay? But when you add antacids, what's it doing? It's raising the pH, okay, kind of neutralizing the acids so you don't have that low pH environment. So people who take lots of antacids in their body, especially women, because y'all have to add on that menstrual cycle, you can end up becoming a iron deficient anemia. Okay? So we'll talk about that later on. Another thing I do want to mention too, all right? So I know some of us are a little bit older in here than others, but something happens like when you reach a certain age, about 60, 65, that your appetite actually goes down, okay? So like my mother-in-law will eat like cereal for supper, or like some cottage cheese and those kind of things. It's like weird crap. And it's all because she said, I'm not hungry, But she actually developed so severe of iron deficiency that she ended up having to have iron transfusions. Like they had, put iron in IV in her body instead of just giving her supplement. In other words, the pills weren't enough to compensate for her iron depletion. Okay, So that's one of the things I do want to encourage you when you do get older. I don't care, you know, I know y'all got a long time, but you know, some of us is getting close to that age. Still try to eat some meat. You know, at least once a week, have a burger or, you know, something. And that way you kind of do help with the iron deficiency. Because diet plays a big role in it, like we were talking about here. Okay? Questions about that, guys? All right. Heme iron is more readily absorbed because of this. So those gastric, and so really, I guess I misled you guys. I didn't really mean to mislead you. So the non-ferrous iron is what is, so like iron 3 is hard to absorb. But remember, we still have to have iron 3. We have to have iron 3 for enzymatic reactions that take place. And some of those enzymes play a role in converting iron 3 to iron 2. Okay? So that's the reason why they become iron deficient in those sense. It's not necessarily that they're absorbing iron, not absorbing the heme iron, but they still have to have those non-heme irons, so the iron 3s as we go. Okay. Negative correlation between iron absorbed and amount stored. So when it talks about a negative correlation, it's talking about a negative feedback system. And y'all remember that from biology? You guys talk about negative feedback systems. What's the best analogy of a negative feedback system that everybody's familiar with? A what?
Stereo.
A stereo? What?
You said negative feedback.
I know. That's what it is. What's a negative feedback? Y'all, does everybody have a heat and cooling system in your house? Some sort? Huh? Your heating and cooling system works on a negative feedback system. So you have a thermostat, and you set it at a certain number, right? So if you set it on 72, okay, it should be hot. It will never be at my house, you know. 72, okay, if the temperature drops below 72, say we're in the air conditioning, we got our air conditioning on, drops below 72, what happens to your air? No. Now if it drops below 72 or at 72, it does what? It cuts off, right? Because that's where that's your optimal temperature. Because that's what you got it set at, right? Okay? But what if the temperature in your house goes up to 74? What's going to happen to your air conditioning? Then it's going to cut off. And it's going to run until the temperature does what? Gets back to 72. Okay? That's a negative feedback system. Your glucose works the same way on a negative feedback system with insulin and glucagon and all these other systems or all these regulators. Okay? But your iron works the same way. So my body says I have to have, you know, between 40 and 50 milligrams. Is it milligrams, like milligrams per kilogram? Or is it grams? Grams per kilogram and body weight. Is that what it was? So my body says I got to have that 40 to 50, and if it goes above it, I stop absorbing. If it goes below it, then I absorb more. Does that make sense? So that I can kind of keep that pool constant, so that I can make hemoglobin. All right? That makes sense? Okay. Also, anything that affects erythropoiesis. Okay. So like I have a acute blood loss. All right. Kim gets stabbed in the throat. She has to go to the ER. There's blood squirting out of her throat. So she's losing units of blood. Her body is going to do what? Decides to go in shock. Well, it's going to try to plug up the hole, of course. But what's her bone marrow going to automatically start doing? Making more red blood cells, right? So what's going to happen is she's going to start increasing erythropoiesis. So if she's increasing erythropoiesis, she's also going to increase iron regulation. So in other words, she's going to start depleting her iron pools, because if she's laying on the table with her neck chopped open, she ain't going to be eating a steak, right? So eventually she could actually, blood loss leads to iron deficiency anemia, because your body tries to compensate, so it ends up using all your iron stores, okay? That's the reason GI bleed, people who have GI bleeds, they'll actually a lot of times have anemia that kind of looks like iron deficiency. And it really is iron deficiency, but it's not because of absorption or anything else. It's because of the loss of blood. Okay? As we go. All right, so this little diagram kind of shows you how iron is absorbed through the enterocytes. Yeah, I don't know if you guys know this or not. Enterocytes have pili, so they have little feet-looking little projections on them. It just increases the surface area. This is essentially what it does. So there's more room to absorb. So you guys kind of need to look at that as you get a chance to. Okay?
Do we need to know about like the proteins and the ferric reductase?
Yeah, you got to give me a minute though. Give me just a minute there, sunshine. I'm getting there. You're reading ahead too quick. Damn Yankee.
These are my notes.
Well, I don't need your notes. I need my notes. You got to give me a minute. Bioavailability of iron, of course, is very important. That's what we're talking about with diet, these kind of things. And those macrophages to be able to do the recycling. That also plays a role in the amount of iron that we have, and it affects the absorption in the GI tract. Condition of the mucosal cells in the GI tract, so the enterocytes. So if you have people that have cancer of the colons, you know, those kind of things affect how they absorb iron. Okay, and then there's lots of other things you guys can look at here. You can kind of read through these to kind of understand what absorption takes place. Okay, so let's talk about transferrin. All right, iron transport, transferrin. Okay, so transferrin, plasma iron transport protein that mediates iron exchange between the tissues. So in other words, it's going to bind to the receptor sites. Okay, it's a single polypeptide. Okay, so like we talked about, hemoglobin is a quaternary. You know, it's got 4 basically tetramer. It's a tetramer, so it's got 2 dimers, 2 alpha, 2 beta, 2 alpha, 2 gamma, depending on which one we're talking about. In this case, transferrin is just a single protein, one protein to get by itself. Okay, it has 2 homologous lobes, so which what we're talking about here. So it's a single bar-looking protein, and then on its ends it has iron. So essentially, transferrin can carry 2 iron molecules. Okay, all the time. Okay, so each lobe contains an iron binding site and can carry 1 molecule of iron or 2 iron molecules. Okay, and we're going to talk about that in just a second. All right. So it is a negative acute phase reactant. All right, so we haven't really talked about this yet. All right, acute phase reactant or acute phase response. All right, anytime. What does acute mean? Sudden, onset, just all of a sudden. So like a while ago we talked about Kim getting stabbed in the throat and she starts bleeding. That is an acute problem. Okay, she don't just normally have that. So what would happen is she would be bleeding in that acute stage. So what's going to happen to her transferrin? It's going to drop really, really quick. Okay. There are other acute phase reactants that we're going to talk about later on. It's in clinical chemistry in the fall. There's actually, y'all guys know what a protein electrophoresis is? Have you ever heard that term? Electrophoresis. You know what electrophoresis is? Well, let's go ahead and talk about that right now. So y'all should know what electrophoresis is. We're going to talk about that in the next chapter. All right, so look. So you have a chamber, okay, like a little plastic, looks like an aquarium. I know that's down a bit smaller, like a little acrylic plastic thing that has fluid in it. Okay, usually there's like a shelf, like so you lay something on top of it. Okay, and you have augers or media, certain types of media. Okay, there's cellulose. There's a cellulose one. There's an acrylic acrylic form that you use too. They've got different names, and we'll talk about that later on. Doesn't really matter. So you make your auger, okay, and inside, in here, you put a liquid. It's an electrolyte, okay, and then here you have a positive charge and a negative charge, okay. It's actually known as a anode and a cathode. All right, now listen. That is confusing as crap because we talk about ions, we talk about positive being cations, what? Cations. And then we have negative ones that are known as anions. Anions. Yeah, I think it's right. We'll go right. Anion. Well, I had it right then. Just didn't look right. Okay? Either way. But if you look at this, they're right the opposite. The positive pole is known as an anode, and the negative is called a cathode. Okay? And here's why. All right? So in life, who attracts each other? Opposites, right? So even though this is the negative charge, it's actually attracting the cations. So they call it the cathode. Does that make sense? And then the positive is going to attract the negative, so they call it the anode, okay? Or anode, whatever how you want to say it. All right? Does that make sense? I know it is confusing. It really is confusing. It's always been confusing to me, okay? But anyway, so basically, right, so we put voltage to this. We know we're going to get a flow of electrons like this, right? That's the way electricity flows, okay, through there. Send those little electrons, okay? Here you have little wells that you put your sample in, all right? You have certain pHs. You have a pH anywhere from 6.8 to 8.6, depending on which one. Okay, I'm going to say or, all right, because that's usually what it is. One of them's 6.8, one of them's 8.6. All right, so in the 8.6 one, when you expose a protein, no matter what it is, okay, most proteins are actually negatively charged anyhow, but at a pH of 8.6, it makes them negative, no matter what, okay? So, if these are already negatively charged, where are they going to be attracted to? They're going to be attracted to the anode, okay? So, toward that positive side. So, based off of their size, okay, how big they are, how small, they're going to migrate in a certain pattern to that positive side. Does that make sense? Once I stick it in this chamber here, okay? So based off of this, I can separate proteins by their charge, but also by their size, okay? Bigger ones are going to move slower. So larger proteins move slower, so they make a band close to the origin, okay? Things that are light, small proteins, are going to move really, really fast, so they go quicker and further through the auger. Okay? Does that make sense? All right, listen to me very carefully. This concept is very important when we start talking about hemoglobinopathies in the next chapter, because this is how we diagnose hemoglobinopathies. Okay? Protein electrophoresis. We actually call it hemoglobin electrophoresis, but it's the same concept. Okay? So,
How do you spell
electrophoresis. I think that's right. Yeah, that looks right. I have to write crap down, but I'm pretty sure that's right. Electrophoresis, yes. electrophoresis. I think that's right. It's close, isn't it?
That's right.
Okay. All right. So, what's going to happen later on? We're going to talk about protein, just different proteins, and then you get a band. So, in other words, you put this in a computer, and the computer looks at the density and the amounts of these bands, and then it corresponds it into a line, okay? This is albumin because albumin is the largest amount of protein that we have in our body, okay? This one is a group known as alpha 1, alpha 2, beta, and then you have a gamma, okay? From here to here are acute phase reactants. So in chemistry, I'm going to tell you all the alpha 1s, all the alpha 2s, all the betas, and then the gammas you know because this is antibodies. So IgG, IgA, IgM, IgE, and IgD. Y'all remember that? Okay? So this is important, but right now, you just need to understand that these are acute phase reactants. Okay? So, transferrin is in the alpha 2s. Okay? So if you had somebody that had an acute phase reacting going on, inflammation, bleeding, those kind of things, you would see kind of a decrease in that line there because they decrease in acute phase reactants. Does that make sense? If it doesn't make sense now, it doesn't really matter because it will make sense when we get to chemistry. Okay? All right. Total iron binding capacity, TIBC. Very, very important concept here. You do these every day in the lab. Okay? We're going to talk a little bit more about this in clinical chemistry, but this is part of it. Okay? Total iron binding capacity. So what does that mean? That basically means how many spaces are available. Okay? So we said we have transferrin. We want to know how many spaces are available. So in other words, TIBC is measuring how many irons are not there on the transferrin. Does that make sense? Because this is iron binding sites. Okay? So we're looking to see how many of these are open. Okay? If we have a bunch of them open, what does that mean? It means iron deficiency. I mean, because these guys should be full and being taken to the inner site. I mean, well, not the inner sites necessarily, but from the inner sites to the erythroblast. Okay? So 250 to 450 micrograms of iron per deciliter of plasma is what we should have for TIBC. Okay? Serum iron concentration. So the actual concentration in the plasma is what we're looking for, or the serum. Okay? So this concentration of iron is determined by iron release from macrophages. Okay? So this is like recycled iron. Does that make sense? Serum iron level is recycled iron. Alright, so if we had a person who has a hemolytic anemia where they're popping red blood cells, what's going to happen to my serum iron level? It's going to go up, right? Because those macrophages have been popping cells as we go. Okay? 95% complex with transferrin, which is what we need. We need those irons to be bound to transferrin. Alright, questions about that, guys? Alright, so transferrin saturation. Alright, so about 1/3, 33% of transferrin is saturated with iron. Okay, so that means that 33% ought to always be like this. It ought to be full. It ought to have those binding sites. Okay, should be bound. Alright, so that means that what? 66% is not saturated. So there ought to be some binding sites for these iron molecules. Okay? So you look at this, serum iron divided by the TIBC times 100%, or 100 gives you the percent transferrin saturation. This is a calculation that your machine will do. Okay? So what we do in the lab is we measure transferrin levels, TIBC, and iron levels. And then we get the calculation for the percent transferrin saturation. Okay? This all indicates erythropoiesis, what's going on. Okay? So how much iron you have available for erythropoiesis. Alright? Serum unsaturated iron binding is known as a UIBC. So we have TIBC and UIBC. Okay? UIBC is basically reserve iron binding capacity of transferrin. So this is the amount of transferrin that doesn't have any iron on it. Okay? Or at least a binding site. So how do you find TIBC? Or the UIBC, you take the TIBC and subtract serum iron, and then that gives you UIBC. Okay? Unbound or unsaturated iron binding capacity. Okay? A lot of old texts call it unbound. Unbound iron capacity. Okay? So it just essentially means how many of those transferrin molecules have an open spot on them. Okay? You have 2 open spots or 1 open spot. Okay, still there's a place for iron to bind. All right, questions about that, guys? All right, so iron in excess of physiological requirements, it's usually deposited in the tissue for storage, which is primarily the what? Liver. That's right. So storage of our iron is usually in the liver. We do store iron in our bone marrow also, but it's stored in bone marrow where? Where's it stored in bone marrow at? Well, yeah, but where in the bone marrow? Where would iron be stored in the bone marrow? Where do we need it? Where do we need iron in the bone marrow? In the red marrow, in the which red blood cells? What are they called? Erythroblast. That's exactly right. That's where it's stored. Okay? That's the iron that we just have normally. That's our normal iron storage. Notice what it says. Iron in excess. Okay? So anytime iron is stored in the liver, and there's actually some there, but you consider it excess iron. Okay? If it's stored in the liver, it's considered excess iron. Okay, so let's talk about the iron cycle. Okay, iron cycle in general, transferrin to erythroid marrow, to RBCs, to macrophages when senescent RBCs removed and degraded by the liver, spleen, or bone marrow macrophages. And that's kind of your iron cycle. Okay, so basically your iron cycle transferrin, of course, is coming from where? What's transferrin necessary for? Transport from where? The enterocyte, so our intestines. So this is basically absorption, right? So we absorb it in our enterocytes or in our digestive system. It binds to transferrin. Then transferrin transports it to the red marrow, which is what we talked about before, the erythroid marrow. Then, once it gets there, it is given to the erythroblast, okay, and put into the RBCs. Then when the RBCs become sessile, which means they're old and not doing what their job is, macrophages then break them down. We recycle iron, and then it gets sent back to either the liver, spleen, bone marrow, and mostly back to the bone marrow for storage in the erythroblast. Okay? All right, here's your good little picture of the daily iron cycle. Kind of see this, kind of know what's going on. Okay? So we do lose a little bit of that iron. We talked about that earlier, and it's about 1 milligram is about all we really lose. So really and truly, we should only reabsorb about 1 milligram a day of our iron, okay, as we go. Questions about that, guys? All right, so let's talk about iron transport. So transferrin receptor 1, CFR1, these are important receptors that are on the cells for us. Okay, everybody get this stuff down? Hope so. I'm racing it. We'll talk about more about electrophoresis later on, but you do need to at least know what it is. I'll save me a little time in the next chapter. Okay. All right. So transferrin receptor 1s. So basically, you got your cell here. Okay. And then on the cell, you have a receptor, okay? There is a 1, and then there's another receptor that's shaped identical, that is a 2. We'll talk about it in just a little bit. But these are basically where transferrin hooks up on the cell, okay? So the the erythroblasts are going to have lots of these, okay? Lots of spots for them to hook up and bring you the iron, okay? So that's what's going to happen. Transferrin's got iron. It's going to hook up with the receptor. Once it reads it, it drops the iron off, and then transferrin leaves as UIBC, okay? So it's just free transferrin at that point, okay? Unsaturated transferrin, and it goes back out, okay? And then iron, of course, is put into the cells to go to the mitochondria to be used for heme production, okay? As we go, all right? So expressed on virtually all cells, but especially those erythroblasts, okay? All right, so transferrin with the TFR1 complex enters the cell, iron's released. At this point, okay, this is a new term, apo, okay? Anytime you see apo as a prefix, it means unbound, okay? We're going to talk about apo a lot in clinical chemistry when we get there, okay? Apotransferrin, okay, means transferrin that's not bound with iron. Apotransferrin, okay? So basically then they're available for recycling as we go. All right. There is also a transferrin receptor 2, and its job is also to bind transferrin. It just does it less efficiently, okay? These are found on the hepatocytes, the duodenal crypt cells, and erythroid cells, okay? And it's not the duodenum. I know that's what how it's spelled and what it looks like. The duodenum is part of the small intestine, but it's actually pronounced the duodenum, okay? So this is the duodenal crypt cells, okay? But it does mean the small intestine, all right? Is what it's essentially talking about, okay? And it plays a role in regulating your total body iron. That's about all I want you to know about those, okay? Questions? What time is it? About 9:36. All right, let's go about 10 more minutes if we can, if y'all can make it 10 more minutes. Ferritin. So let's talk about ferritin. So ferritin basically is iron storage, okay? So one ferritin molecule has about 4,500 molecules of ferric, right, with the iron 3. We don't care about the iron 3. We need it to be in iron 2 form, right? But this is, ferritin is iron storage, and the majority of iron stored is actually in the ferric stage, which is the iron 3, okay? This is the primary storage compound of iron, all right, ferritin. All right, what's the other primary form of iron storage? Hemosiderin. There you go. Okay, this one is readily available for erythropoiesis. Even though it's in the iron 3 state, it is still available. So an enzymatic reaction will occur, will oxidize it, basically drop it down to iron 2, and then it can bind to heme. Okay? Found in the bone marrow, the liver, the spleen, and usually within cytorosomes. And these are cytorosomes, are little packets of iron in those cells. Okay? This is the main index of iron stores. Okay? Apoferritin is ferritin without iron. Okay, so ferritin is like a protein that is basically holding on to a bunch of them. Okay, all right. I think this is how you spell it. How you spell micelles? I'm talking about micelles. Have y'all heard that? I've seen this the other day on a commercial. There was a commercial on talking about a shampoo. It's talking about contains micelles, you know. And I know people don't know what micelles are, but is that how you spell micelles? Huh?
If this would load, I would let you know.
I think it's pretty close. It may not be exactly.
There's 2 L's.
There's 2 L's? Okay. 2 L's. Micelles. All right? So we're going to talk about micelles in clinical chemistry also because cholesterol is actually transported as micelles a lot of times. So essentially what it is ferritin, okay, is a protein, of course, so we know it's going to be kind of shaped like this because that's how proteins are formed, right? Okay? Then you essentially have a bunch of, well, 4,500. We're not going to do that. But you have this, basically surrounding it is iron molecules. And so when you have a protein and then have bunches of things attached to it around it, it's referred to as a micelle. Okay? So like in your shampoos, when you see micelle, it's usually something that has little things bound to it in it. So it's usually like proteins and waxes and those kind of crap in shampoos, sulfides and those kind of things. Okay? But these are known as micelles. So ferritin is a form of a micelle. Okay? So ferritin protein, and then you have all those irons surrounding it. Okay? This is a number you need to know. 4,500 iron molecules. Make sure you know that number. Okay? So when you have ferritin without iron, it's known as apoferritin, just like what we talked about earlier. Okay? Apo means unbound. Something. Okay? All right. The other form is hemosiderin. Okay? The hemosiderin is usually found primarily in the macrophages in the bone marrow. Okay? The difference is where ferritin, okay, is a protein, then it has all the iron bound around it. Hemosiderin is iron, carbohydrates, lipids, and proteins. So it's a micelle also, but it is a micelle that contains lots of different organic compounds, okay, with iron being the majority, okay, as you go. All right, hemosiderin. So ferritin, hemosiderin. Storage, right? What transports iron? Huh? What transports iron? Transferritin. Thank you. Ferritin is iron. That's the iron store. Transferrin is what transports it. It's got trans in it, guys. Anytime you see the word trans in something, it means to carry. Okay? All right, so hemosiderin, iron from hemosiderin is released slowly, so it's like a time release kind of thing. So it's not readily available for cellular metabolism. Bone marrow macrophages contain hemosiderin. If iron stores are normal or increased, this is what we look for when we're staining with Prussian blue. Okay, most of the time, I'm not saying all the time, but a lot of times, iron stain is part of a bone marrow aspiration. So we used to do these. Still hospitals do them. They're called cytochemical stains. So cell stains is what cytochemical means. One of pearl Prussian blue is what's usually used, is actually a cytochemical stain, but it stains specifically for iron. So we want to see how much iron is in those erythroblasts on the bone marrow to see what's going on, okay? Because that's one of the things they'll also do, guys, and we hadn't made mention of this, but they will. If a person stays iron deficient, anemia all the time, and they can't figure out and can't fix it with iron therapy, the next step is to do a bone marrow aspiration and look at the erythropoiesis that's going on and make sure that the erythroblasts have iron in them, okay? And if they don't have iron in them, then we know that there's definitely an underlying condition that's going on, okay, as we go. All right? So it's a good chart to know right there. Storage forms of iron, kind of know what they are and what their levels should be, okay? All right, so this is basically showing you how iron is absorbed. It's a good little chart, a little flow chart, kind of lets you know how things are going, where iron goes, when it gets transformed from iron 3 to iron 2, those kind of things. So this is a good little figure to look at. Okay, it's very self-explanatory, so there's no reason for me to talk about it, but you can look at it and kind of figure out what's going on. Okay, All right, same way here. This is talking about bringing the iron into the macrophages and storing it and those kind of things and what it does. All right, so we'll stop right there. Iron balance is a good place to stop.